I want to wait. How long do we have to wait until we're down to less than 1% of whatever we had impure-wise in our pond originally? Is that fair? Until we're down to less than 1% of the original impurity level. Is that fair? I'm thinking. So I'm thinking we need. Let's go over here. This is really small, but I think we can probably get the idea. I'll write bigger. You guys are cool with the camera shooting across you like that? No? We can. I can do little emoticons over your faces later. Actually, no, I can't. You're all weekend doing that. Go ahead. Aha, we have a vote. We have a vote for 6 hours. Well, let's figure this out. So, what I want to do is let's create a sequential look at what's going on, okay? So let's say X is number of hours that have passed. We'll say number of hours passed. And then Y, what do you think Y should be? What do you think Y should be? Percent of impurities that are remaining? I love that. So percent impurity remaining. I love that. It's a great idea. Was anybody concerned that I didn't tell you how much impurity was in the pond in the first place? It doesn't. Beautiful. Hold that thought, Kurt. Yes. That A value that's over there? I got it. Remember how it's right here. Both sides. The A value that we had for 38 back here, we don't actually have to have, we didn't have to call that A. We could have just called that 1. 1 for the entire class. We had one class that each had pennies in their hand. After one iteration, how many then had flipped heads? Percentage-wise, half of them, 50% or half of them. Now, we said that was equal to roughly, 19 people. But that's half of 38. You could just say half of the class. And then after the second flip, how many do we have left, roughly? A quarter. Now, we said exactly 8.5 or whatever, it was 9.5 or 10, whatever it was. But you could also say just a quarter of the original class had flipped heads. And then an eighth of the original class. So what we can just say is, at 0 hours, there's 100% impurity remaining. You can put a number in there if you want to. Say you know or you think that there's like 200 pounds of fish goose poop in there. But just say 1. 1 stands for 100% of the impurities remaining. That make sense? We'll start with that. So your A is 1, if you will. Your A is 1. Okay. How about 1 hour? What percent impurity is remaining? 30%, correct? 0.3 is now remaining. So at 1, you've got 0.3 left. Because if you want to say mathematically why, and it's probably not right here because you can figure it out. Well, if it removes 70%, that means it's leaving 30% behind. What you're starting with is you're starting with that 1, and you're dumping off the 0.7. You're dumping off that 0.7. So you're left with your 0.3. Is that fair? Is that fair? Good. Excellent. Okay. How about after 2 hours? What remains after 2 hours? What remains now? Say that. Kate, go ahead. Why? How are you getting this? Walk me through the process. I don't care as much about the number, about the process right now.
You take away 70% of 0.3.
Right. It removes. So you start, basically, let's see if I can walk through this. We start now with 0.3. This is your new starting value. This is what's called recursive relationships. If your starting value keeps changing each time, it's recursive. So we started with a 1. 1 became a 3. Now we're starting with a 3. What's 3 going to become? Well, we have to take away from that 0.3, right? From that 0.3, we now have to take away 70% of that 0.3, don't we? 70% of that 0.3 taken away. Is that fair? You guys buy that logic? Ish? We're getting there? Okay, good. So now watch what happens here. Can I use a little bit of algebra? You can do this arithmetically if you want. A little teeny bit of algebra, maybe. This might piss you off a little bit, but I don't think so. You see how both of those have a 0.3 in them? I want to pull the 0.3 out. Factor it out. What do I leave behind here if I did that? Be brave. I'm hearing it.
-0.7.
1 and a negative 0.7. So here I leave a 1 behind, minus Lynn, 0.7. Friends, which 1 minus 0.7? 0.3. So this is 0.3 times 0.3, or 0.3 squared. Is that coincidence? No!
Of course not.
It has to be, because rather than thinking of it as we're taking away 70%, think of it as we are leaving 30%. Remember how we defined it? We defined it as the percent remaining. You guys are figuring it out by figuring out how much to take away, but think of it a different way. Think of it as how much is left behind. It's like when you go to the store and they say, dude, jeans are 80% off. So everybody goes, okay, so they were originally $100. I'm taking 80% off, that's $20 remaining. Or you're just paying 20%. You can go at it that way too. That's kind of what this is doing. Is that, you okay with that? Is that fair? So 0.3 squared, what's that, 0.09? Did I do that right? So now you're down to what? Now you're down to what? As a percentage, what is that? 9%. So you started at 100%, then you were at 3%, now you're at 9%. Notice that's not a constant first difference. From 1 to 0.3 is down by 7, from 0.3 to 0.09 is down by 0.27. You're not getting a constant first difference. We'll come back to that momentarily. Ready for 3 hours? Are we okay so far? Is this okay? Did the algebra piss anybody off? I don't mean to piss people off. Let's do a couple more steps, then we'll take our 5, because you are starting to get that lazy look. But I also want to keep this running. I want to keep this running while you got it fresh in your mind. Let's go to 3 hours. Yes? What's our new starting point?
0.09.
Yes, our new starting point is what is remaining after step 2. So that's 0.09. With your permission, I'm going to take away 70% of that 0.09. Correct? Does that make sense? I'm taking away 70% of that 0.09. Again, with your permission, I'd like to put a little bit of algebra in this. A little permission. I'm always asking for permission because I want to piss you guys off. 0.09 is 0.3 squared, right? This is 0.3 squared minus 0.7 times 0.3 squared. All I did was I changed the 0.09s back to 0.3 squares. Is that fair? Fair enough? Can I factor out that 0.3 squared, the same trick I did last time? You mind if I factor that out again? Is that okay? Yes. 0.3 squared pulled out of both these pieces of this binomial. What's left here? Minus. What's 1 minus 0.7? 0.3. So this is 0.3 squared times 0.3 PJ, repeated multiplication. This is, say it loud.
0.3.
This is 0.3 cubed. Is there an ignorable pattern here? Or is there a beautiful pattern here? I'm seeing after the 3rd hour, I have 0.3 cubed left. 0.3 cubed, is that about, what is that? What is that, about 3%-ish? What does that come out to be? 2.7%? Now we're down to 2.7%. But I'm not so concerned about that right now. I will be momentarily concerned about that. But I want to look at this pattern. After 3 hours, there's that much remaining. After 2 hours, there was that much remaining. After 1 hour, that much. After 0 hours, that much. I'm going to write this in a different way if you don't mind. Isn't this 0.3 to the 0 power? You seeing a pattern there, friends? You seeing a pattern in what's remaining? Hell yeah, you are. You just figured out the model, didn't you? If y is the percent remaining, just like we set it up over here, if y is the percent remaining, what's it equal to? I'm going to put a 1 out here just to keep it the 1 pond full of impurities. 0.3 to the what power? To the x power. That's your repeated multiplication. This is the definition of an exponent. Repeated multiplication. Every hour that passes, you multiply again, and you multiply again, and you multiply again, and you multiply. And eventually, this number that's out here will do what? It will become as small as you need it to be, and in this case, we're interested in when it becomes less than 1%. Please, Kate.
Weird logical question.
Go ahead.
If we're removing impurities, the way we're doing it, we will obviously never get to 0.
Can't.
In actuality, you would eventually get to 0.
That's arguable. See, this is the same thing that happens with drug studies. Have you ever heard of drugs becoming residual in your spine? Like you take certain drugs and they become residual in your spine forever. Arguably, drugs have a half-life, which means the amount of time it takes for half of the drug to go away. So if you take aspirin, I think aspirin has a 4-hour half-life. I think I might be making this up, but it's from memory, so I'm not trying to make it, I'm trying to be accurate. Aspirin has a 4-hour half-life. You take 1,000 milligrams of aspirin now at 11 o'clock, okay? At 3 o'clock, how much aspirin is in your system? Half of it, so 500 milligrams. At 7 o'clock, how much? 250. Well, a quarter, so 250 of the original 1,000. At 11 o'clock again, 125, 12.5%, 125. At 3 a.m., you're down to 62.5%, then roughly 30%, roughly 15%, roughly 7%, roughly 3.5%, then 1 2/4. So what Kate's saying is it's never going to get to zero. My retort is it will get to zero enough. Yeah, it'll never completely go away, but it'll become such a small amount left that it's essentially not there anymore. Our bodies pick up stuff. Our bodies are full of contaminants that we've been exposed to our entire lives. I mean, just environmental contaminants. Have you ever thought about this? Just existing in the world. You pick up environmental contaminants all the time, and your body does a great job of sloughing them off. But there's always the residuals left in your body. And the kicker is, eventually they get down to a low enough amount that it's essentially as if they weren't there.
But in some cases, like dropping a pen, it does get to zero.
That's a limiting value. You're talking about a calculus, not a liver. Calculus, perfect. Now, you got to remember, calculus is trying to describe using perfect mathematics the reality of the world. Yes, it does get to zero there. But if your filter, if your liver or your pond filter is working by removing 70% of the time, it can't get to zero mathematically. It just gets asymptotic with zero.
It probably gets too small for it to keep it moving.
That's what I'm talking about. Well, that's arguable. That's a good argument. It gets to be such a small amount that the pieces of the filter can't even process it. And then you can essentially say it does level off. But you can't get to zero in that mathematical argument. It's a great point, Kate. It's a great point. Let's take 5. Great points. Please, go ahead.
Do they use that process of reverse engineer for carbon-14 dating?
Yes. Well, actually, it's the same process. It's just that the carbon-14 is the half-life.
Okay.
It's exactly the same thing. And we're going to come back to that and look at the growth of this. Let's take 5, though. You're getting that glazed look. We'll answer this question. We'll answer how long it takes to get down below half. We'll use our TIs to help us do it, too. I think that's a good use of technology. And we'll play. But go take 5. The room is getting a little warm. Continue it. Graphic look. Point 3, well, what was point 3 before? Is it small enough? Let's get it to 1. Just continue it. That's what I'm saying. We're going to use the model. This is where, once you understand, no, I don't think we should keep doing it this way. I think we let technology do it infinitely for us. Exactly. Good. There's not like whiteboards. Well, no. I got that side over there. I haven't got to it. I want to, speaking of whiteboards, thank you for saying that. I got the wall. I noticed that my marks on the wall from last time got erased.
Oh, they did?
They did. Yeah, I hope that's visible enough. Here, let's just do this. In case you're watching this at home, we'll do a little flyby. Hello! Hi!
Hi. Did you
Come with me.
realize that you went to
What did I do?
class yesterday morning? And
No, I forgot to tell you to slide it under my door when you were done,
Okay,
which
well,
you
that's what I
did.
Okay, good.
I always do that. I always do that when you guys are taking exams when I'm in my office, because I just figure you'll disappear and you go to your class.
Okay.
So you did the right thing, Sherilyn.
Okay, thank you.
You're good. All right, here's our work. There's our model. There's Roy.